Hello, and welcome back to the course on classical electromagnetism. We are still on the sixth chapter for this course, and this is the second lesson for this chapter. So before we proceed, let us first review some concepts. So we have discussed about the concept of electric potential, and this is if there's an electric potential difference between 2 points, then there is an electric field causing that potential difference, E dot dl. So this is actually from point A to point B, the positive to the negative potential. So we already also have discussed force on current carrying conductors. So if you have a current carrying conductors and it is exposed to an external magnetic field B, then that current carrying conductor will experience a force equal to this integral, I cross B dl. So for this lesson, we will be talking about EMF. It's actually just an abbreviation, but I don't like to spell it out because it will be confusing. So let's just say EMF. So EMF is the potential responsible for current to flow uphill inside a source. So EMF was originally called, or is the abbreviation for electromotive force, but as you can see, it's a potential quantity, meaning its unit is volt. So it's not a force. So let's not use its full word, which is electromotive force. Instead, let's just say EMF, because this is one of the poor terms in physics. It's not a force, it's a potential. So it would be much suitable if they call this electromotive potential, but no, they call this electromotive force or EMF. Anyway, let's not use the word force, just EMF. So it's a potential responsible for current to flow uphill or against the internal electrostatic field in a source. So, for example, you have a battery and you connect it to an electronic device. So current flows, conventional current flows from the positive terminal, while the actual current is actually electron current. It actually flows from the negative terminal. So in analyzing circuits in your basic electromagnetism, you actually are always using conventional current because that is already the convention set by the electrical engineers. So we can't go against the convention. So inside the battery is actually an EMF and an internal resistance. So the EMF is this symbol. It's a Greek letter C, but let's not call it C, but just EMF. So this is the symbol for EMF, and the small r is the symbol for internal resistance, and this is usually very, very small. So you will notice that there is an electrostatic field. So since this is the positive potential, this is the negative potential, then there's an electrostatic field in that direction. And if you have a conventional current, which is assumed to be positive charges, then the charges will be forced in the direction of the field. But take note that the current or the positive charges are actually flowing in this circuit in a counterclockwise manner, meaning this charge will move to the left. So the reason that it's moving to the left, it's because of the EMF, because the EMF generates a non-electrostatic field. So the N subscript here corresponds to non-electrostatic. The E subscript here corresponds to electrostatic. So there's a non-electrostatic force that's pushing the charge to the left. So if you have an ideal source of EMF, meaning there's no internal resistance, R is 0, small r is 0, then the total force, the two forces, the non-electrostatic and the electrostatic force, will actually balance each other out, meaning a charge can move in the circuit with uniform velocity. It will not accelerate. So it will still move to the right because it still has a momentum to the right when it enters the battery. But if you have, and in this case, the voltage of the battery is just equal to its EMF. But if you have a real source of EMF, the internal resistance is no longer zero, then the non-electrostatic force overcomes or is much greater than the electrostatic force. And in this case, the potential of the battery is just the EMF minus I times R. But take note, if there is still no current I flowing through your battery, then the EMF of your battery is still, a real battery is still that one. It's just equal to the EMF. So if you have a battery and you measure its potential without connecting it to a circuit, then the value that you will get is actually a higher value, and that is actually the EMF. Now, when you connect the battery to a circuit, meaning there's now a current flowing through the battery, and that value that you get when the battery is not connected to the circuit will now be lesser, because it will be subtracted by an amount I times I times R. So that's why when you measure the voltage of a battery, when it is not connected to a circuit and when it is connected to the circuit, you will have different values because of this term minus I times R. So we have what we call a motional EMF. This is the EMF induced due to a motion through a magnetic field. So suppose you have a conductor of length L and you expose it to an external magnetic field B. In this case, it's directed into the bridge, and you move the bar in this direction, with the velocity V. So what will happen is the charges in the bar will experience a magnetic force equal to QV cross B, and meaning if you take the cross product of V cross B, so the positive charges will actually be pushed upward and the negative charges will be pushed downward, and this creates a potential difference. So the upper part of the conductor is now a positive terminal, and the negative and the lower part of the conductor becomes a negative terminal, essentially making the conductor a source of EMF, or essentially a battery. So in that case, there is an electrostatic field from the positive, directed from the positive to the negative terminal, and that electric field is due to the induced EMF. So your conductor now becomes a source of EMF, essentially a battery. So the EMF, the motional EMF induced in this moving conductor is given by E dot dl, where E is the induced electric field, this electric field. And in this case, the induced electric field is actually just equal to V cross B. So the induced EMF is just the V cross B dot dl. So in this case, where the velocity is perpendicular to the magnetic field and to the length of the vector, this actually just reduced to VBL, VB times L, velocity times magnetic field times the length. That's actually what you have in your basic electromagnetism. So there is a flux rule for motional EMF. The induced EMF is actually negative change in magnetic flux with respect to time, and we usually call this rule as the Faraday's law. So take note, the magnetic flux is similar to the electric flux. If electric flux is E dot dA, then magnetic flux is B dot dA. But again, for magnetism, if you take the closed surface integral to get the total flux is always zero, because the total dipole enclosed is zero. Essentially, the total magnetic charge enclosed is zero. So the closed integral of B dot dA is zero, but this is just integral of B dot dA. It is not closed integral. Okay. So this is the magnetic flux. So The negative sign here implies the direction of any magnetic induction effect is such as to oppose the cause of the effect, and this is what we call Lenz's law. So the negative sign here implies that the induced EMF, the direction of the induced EMF is always opposite. Negative means opposite the direction of change of the flux. So another way of saying this is that nature abhors or doesn't like changes in magnetic flux. So if you change the magnetic flux, nature will always react, or nature will always counteract with an induced electric field or an induced magnetic field. So for this example, for instance, you have a loop, a current loop, a conducting loop, and then it's exposed to a magnetic field directed upwards. But this magnetic field is increasing. So if the magnetic field is increasing, by the way, there are three ways for the flux to change. It's either the magnetic field changes, or the area of the loop changes, or since this is a cross product, so this is B dA cosine theta, where theta is the angle between the magnetic field and the area vector. So it's either the magnetic field will change, the area will change, or the angle between the magnetic field and the area vector will change. So those are the three things that can change the flux. So in this case, only the magnetic field is changing. It's actually increasing. Therefore, nature will counteract. It will induce a magnetic field in the opposite direction. And if the induced magnetic field is downward, then the direction of the current and the direction of the induced electric field and EMF is in this direction, so in that direction. So we always use the right hand rule. Take note, the direction of the area vector depends on the direction of the current. So using right hand rule, if your fingers curling are the direction of the current, then this is the direction of the area vector. So in this case, the direction of the area vector is downwards. Okay. So example number 1, this is a slide wire generator. So you actually have discussed this in your basic electromagnetism. So you have a wire, slide it, it becomes there's an EMF induced at the ends of the of this bar, and then basically this becomes a battery. So it's a generator. It can generate current and EMF. So a bar with mass M moves through a slide wire with an initial velocity V0. Find the current flowing through the resistor. Okay. So in this case, before we can find the current, we must first find the induced EMF. So we use the flux rule. The induced EMF is just negative of the change in flux with respect to the change in time. Now, in this case, what will happen is, by the way, these are our coordinates. This to the right is the positive x-axis, upward is the positive y-axis, out of the page or towards you is the positive z-axis. So in this case, our magnetic field is into the page, so its direction is along the negative z-axis. So the velocity is to the right, so meaning along the positive x-axis. So in this case, you have V cross B, so meaning the upper part of the bar will become positive and the lower part will become negative, meaning the current will flow in the circuit in a counterclockwise manner. So if that is the direction of the current, so this is actually a loop. So if that is the direction of the current is counterclockwise, then the direction of the area vector is positive z hat. So in this case, our flux is just integral of B dot dA, but the magnetic field integral of B dot dA, and B is actually uniform at all points in the area of the loop, in the area of the loop. in the area of this loop, in this area, the magnetic field is the same, has the same value at all points in the loop. So meaning I can take it out of the integral, and you will just have B integral of dA, and integral of dA is just the total area. So basically you will just have B dot the total area. So B has a magnitude of B. So our B, assuming it has a magnitude of B, and its direction is negative z hat. Our area vector, say, has a magnitude A. And the area, this is just a square, so the area is just the length of the bar is L, and say this is the width, so it's just length times width, and the direction is actually positive z hat, because the direction of the current is in this direction, so the area vector is positive z hat out of the page. So you have z hat, that is just 1, so you have a negative sign here, and you will get negative BL. So take note, the magnetic field and the length doesn't depend on time. The only thing that depends on time here is the area, wherein the width. The width of this loop is actually increasing because you are pulling the bar to the left. So you will get, okay, there will be no more negative sign because of this negative sign here. You will dW dt. And the different dW dt, the change in width over the change in time, is actually just given by the velocity, V. So VBL. So that one. So the EMF is just equal to VBL. And the current, by virtue of Ohm's law, since there's no, this is our battery basically, and it has no, we will assume that it has no internal resistance, because the resistance is just this one, outside of the circuit, or outside of the bar. Then, it's just, the voltage is just the EMF divided by R. So this is just VBL over R. This is our current. This is our answer for letter A. VBL over R. Okay. Letter B. Find the force on the bar. So you will notice that our bar becomes a current carrying conductor. So current flows in a counterclockwise manner, meaning inside the bar, current will be actually flowing upward. So if you have a current carrying conductor, you expose it to an external magnetic field, then I cross B, B is into the page, and there will be a force in this direction. So the magnetic force will be in that direction. So you will notice that the speed of the bar is actually decreasing. So originally it has an initial velocity V naught, but there's a force in the opposite direction, so it's actually decreasing. The speed of the bar is actually decreasing. Okay, let's find that force. So that force is just equal to L times I cross B. So again, we will assume that the current and the magnetic field along the length DL of this line or this bar is the same. So it becomes a non-integral form. So you have L, the current is just, we have already obtained the value of the current. It's actually VBL over R. And the direction of the bar, current, when it's inside the bar, is upward, so it's Y hat. You cross it with the magnetic field, which is B, and its direction is actually negative Z hat. So Y cross Z is equal to X. There's a negative sign here, so it's negative X. So the force on the bar is just equal to negative V B squared L squared over R, and the direction is negative X hat. Meaning, if this is positive X to the right, then negative X hat is to the left, just as we predicted. So this is not the force on the bar. Okay, letter C. Find the velocity of the bar at any time t. Now, this force is actually equal to the mass of the bar times the acceleration of the bar. The acceleration of the bar is just dv dt, or dv dt x hat. That one. So meaning these two terms here, m dv dt, is just equal to that one. They're both equal. So we equate these two equations for letter C and solve for V. So we have something like this. dV by the way, take note that the velocity is directed to the positive x-axis. So meaning dv dt will also be in the positive axis here. So the acceleration. So you will have dv over v is equal to negative v squared L squared over mr dt, from equating that one. And you integrate. So from an initial velocity to a final velocity, from an initial time 0 from a final time t. And you will get ln of v over v naught is equal to negative v squared L squared over mrt, meaning the velocity as a function of time is just equal to v naught e to the negative v squared L squared over mr, sorry, this is small t, mrt. So v naught e to the negative v squared L squared over mr times t. So at time is equal to 0, e to the 0 is 1, you get the initial velocity. At time is equal to infinity, e to the negative infinity is 0, so the velocity is 0. So there will come a time that this bar will stop from moving. Okay, so that is the velocity. So for letter D, we are asked to find the total energy delivered to the resistor. So we will now use the concept of power, the joule, with respect to work. So power is work per unit time. So meaning work or energy is a power times time. So we integrate this, we integrate that. So we have the total work delivered to the resistor is just equal to, this is the power delivered to the resistor is I squared times R dt. We already know I squared, or I is actually equal to VBL over R. But we also know velocity. Velocity is just V naught e to the negative B squared L squared over MRT. So you have B times L over R. So this is now our current in terms of the in terms of time, the time dependent current. So you square this one, multiply by R, so R will cancel out. So you square that one and then integrate over time. So I will leave that to you, and you will get a value of, is this a surprising value? 1/2 mv naught squared. This is the total energy delivered to the resistor, and this is just equal to the initial kinetic energy of the bar. Because the initial velocity is v naught, its initial kinetic energy is 1/2 mv naught squared. So all of the kinetic energy of the bar is just converted into electrical energy and dissipated or delivered to the resistor. It's actually lost in the resistor. And in that case, when all of the total energy is given to the resistor, the bar now stops from moving. Okay, so that is for letter D. So as a recap for this problem, the current is VBL over R. The force is along the negative x-axis, so in that direction. The velocity is time dependent given by this equation, and the total energy delivered to the resistor is just 1/2 V naught squared, the initial kinetic energy of the bar. Okay, another example. So in this example, we have a square conducting loop, and it's on a table, a distance s from a current carrying wire. So this is our current carrying wire. So find the magnetic flux through the loop. If the loop moves upward with speed v, what is the induced EMF and the direction of the induced current in the loop? If instead the loop moves to the left, what is the induced EMF? Okay, this is the electric field if viewed from the top of a current carrying conductor. So in this region here, take note, if this is the current, this is the direction of the magnetic field. So in this region, the electric field is out of the page or pointing towards you. In this region, the electric field is into the page. So the electric field actually for a current carrying conductor is mu naught I over 2 pi s, and its direction is phi hat. It's curling around the current. So it's inversely proportional to s, the distance from the wire. So meaning these points here, the magnetic field at these points here is weaker as compared to the magnetic fields at closer to the wire. So the magnetic field is stronger if you're closer to the wire, but if you're farther from the wire, the magnetic field is weaker. Okay. So find the magnetic flux through the loop. So the magnetic flux is just integral of B dot dA. This is our B. And our dA, we will assume that our dA is also in the same direction. So let's just consider this loop here. So the magnetic field in this region is actually z hat. That's actually the z hat direction. We'll assume that this is the positive z axis out of the page, the standard z axis. So in this region, inside the loop, the direction of the magnetic field is in this direction. And we will assume, since there's no current still in our loop, we'll assume that the area is also in the z direction. So we'll assume that dA is also dA z hat. It's in the z direction. So if we solve for the flux, magnetic flux, so integral of B dot dA, so you have z hat, that's z hat, so that's just equal to 1. dA, our dA, the differential area of the loop, is actually a square. So the area of the loop is its width is B, and its differential its width is B, and its differential length is ds. This distance is actually ds. So we have ds, and this is a square loop, so that side is B times ds. That is our differential area. This is actually B ds z hat. So integral of B dot dA, this will give you mu naught I over 2 pi mu naught IB integral of ds over s, and we are evaluating s from this distance s to s plus b. So this is s, this is b, so therefore this location with respect to this wire is s plus b. So from s to s plus b, that one. So we get the magnetic flux to be equal to mu naught IB over 2 pi ln of s plus b over s. So that is our magnetic flux. Okay. If the loop moves upward with speed v, what is the induced EMF and the direction of the induced current in the loop? Now, if this loop moves upward, meaning the flux inside the loop will change. Take note, there are only, in this case, there are only two things that will change. It's either the area or the magnetic field. But the area of the loop is fixed. But as you go up, if you move this loop upward, the magnetic field in the upper region is actually much smaller as compared to the magnetic field at points near the wire, because magnetic field is inversely proportional to S, meaning the magnetic field is actually decreasing in that case. So in that case, the induced EMF is actually just negative the change in flux respect to change in time. We already know the flux, so derivative with respect to time of the flux, which is mu naught I b over 2 pi ln of s plus b over s. So we take out all of the constants, we will get mu naught IB over 2 pi. Derivative of ln is 1 over u, derivative of u. So 1 over s plus b over s, derivative of s plus b over s. Differential or derivative with respect to that. So we have s plus b over s is actually 1 plus b over s. So derivative of 1 plus b over s is derivative of 1 over s. You will get negative b over s squared ds dt, where ds dt is just the speed of the loop. So v, ds dt is just equal to v. So I just automatically change it to v. Okay, and you will get the induced EMF is equal to, there's a negative sign, so it's positive mu naught I b squared times v over 2 pi s plus v. That one. So if the induced EMF is positive, meaning the direction of the area vector that you assume is correct. If you get a negative value, meaning the direction of the area vector that you assume, or the direction of the current that you assume, is the opposite direction. So in this case, the current is counterclockwise because we assume that the area vector is in this direction, so meaning the current is in this direction. It's counterclockwise. So that one, we assume the correct direction for the current and the area vector. Okay. For the last question, if instead the loop moves to the left, what is the induced EMF? So if this loop moves to the left, what is the induced EMF? Again, induced EMF has something to do with the change in flux. And the flux, in this case, the only thing that can change the flux is the magnetic field. Now, if the loop is moving sidewards to the left or to the right, the magnetic field, the area of the loop doesn't change. The magnetic field also inside the loop doesn't change because you're just in the same perpendicular distance s. So there's no change in flux, meaning for letter C, there is no change in flux, therefore there is no change in, or there is no induced EMF. So for letter A, this is the flux, this is the induced EMF, the direction of the current is counterclockwise. And for letter C, since there's no change in magnetic field, there's no change in the area, therefore there's no induced EMF. Okay, last example. An alternating current generator, AC generator. So you have a square loop and you mount it on a vertical shaft and rotated at an angular frequency omega. So you have a square loop and it's rotating with an angular frequency of omega. Find the induced EMF for this alternating current generator. So this will actually generate alternating currents that are constantly changing direction. So in this case, we first solve for the magnetic flux on the loop. So we'll use the non-vector form BDA cosine theta. Okay. So since by the way, the magnetic field here is in this direction. Okay. So the only thing that is not constant here, that is changing here, the magnetic field is constant, the area of the loop is constant. The only thing that is not changing here, or is changing here, is the theta, the angle between the magnetic field and the area vector of the loop, because the loop is rotating, meaning the angle between the area vector, take note, the area vector is always perpendicular to the surface of any surface, in this case the area of the loop. So if the loop changes, then the area vector will also change, it will also rotate. So theta, the theta is the one changing here. Okay, so from your previous lessons in waves or rotational motion, the angular displacement is just equal to theta naught plus omega t plus 1/2 alpha t squared. So if we assume that the initial angular position is 0, and if we assume that it's moving at a constant angular velocity, meaning it's not accelerating, there's no angular acceleration, then theta is just equal to omega times t. So that one. Okay, so this will just reduce to b times the total area, which is total area of a square loop with side b is b squared cosine omega t. So this is our flux. So we take the derivative of this with respect to time to solve for the induced EMF of the flux. So basically you have b squared cosine omega t, and you will get positive b squared omega sine omega t. The derivative of cosine omega t with respect to t is negative sine omega t times omega. So this is now the induced EMF. Okay, sorry. So as you can see, the induced EMF is changing with time. It's time dependent, and it's actually oscillating. So that's what we call alternating current. So the EMF values can have a positive value, it can become 0, it become negative, it become positive, it can become negative. So it's continuously changing direction. So meaning it's an alternating current. That's what alternating current means. So you review your concept or your lesson on alternating current. So that is the last lesson for this chapter. So in the next lesson, we will dive deeper into the concept of electromagnetic induction. So we already have introduced the concept of electromagnetic induction. The induced EMF is basically produced by electromagnetic induction. So we'll dive deeper into the concept of electromagnetic induction in the next lesson. So I will see you again in the next lesson.